Yeah, I was going to give a little introduction, but I can hardly think of how to do it better than the way that John has just done. So I did a physics undergraduate degree and really struggled to find it relevant and find it important. And I'm sorry if any of you are doing physics undergraduate degrees, but I was so happy when I discovered climate science, climate change, and the polar regions where I now live. So I live in Tromsø in northern Norway, and it's lovely to visit Canada because people elsewhere are a bit confused when you say you live in the Arctic, but Canada is one of the only countries where you're just another northerner. Like they're not interested in this domestic situation that I have. So today I'm going to talk about the mysteries of Antarctic sea ice. I'm going to give a little bit of background on why I think Antarctic sea ice is really interesting, particularly how it's different by comparison to the Arctic. And then I'm going to talk about the snow cover specifically that sits on Antarctic sea ice, and why I think that within Antarctic sea ice is particularly interesting. And finally, I'll talk a little bit about how we work out the thickness of sea ice from space, and some field campaigns that I've done recently, particularly one where I spent 8 months in Antarctica in 2023, just to reflect on the lifestyle of polar science at the moment, because it's quite interesting, I think. I should say this is sea ice, and I should probably briefly describe what sea ice is for anyone that isn't familiar. So sea ice is what happens when the ocean freezes over. So it's not the same as a glacier, which is made of compacted snow. It is frozen seawater that forms on the surface of the ocean when the air is extremely cold. So sometimes it actually looks like my cover slide. This is a huge sheet of sea ice that I was standing on with my colleague from the University of Calgary, Vishnu Nandan, who's in the photo. This is a glacier. This is not sea ice. This is sea ice. It can be very smooth, can be easy to ski on, can be very shiny. So you can see these crystals formed of deposited water vapor on the surface of the ice. But sometimes sea ice looks like this. It looks like it's covered in snow. It is covered in snow, and it's very rough sometimes. So this is not just snow roughness. This isn't wind redistribution of snow dunes and mounds and hummocks. This is actually an underlying ice roughness formed by bits of ice smashing together like tectonic plates, getting turned over, getting pulled apart. So it's a very interesting material from a physics perspective to study. So I'll start with some background. I'll give you a pitch about why you should not leave the room, why you should care about Antarctic sea ice. And I'll counterintuitively start by talking about the Arctic. So my colleagues at the Arctic University of Norway might be upset with me for saying this, but from some aspects, Arctic sea ice looks kind of easy. So the world is warming at a fairly steady rate, and Arctic sea ice is declining also at a fairly steady rate, right? So this is a graph of the maximum on the left and the minimum extent on the right, how that's changed since we started monitoring it with satellites in 1975. And it's just followed this black dashed line down. And we have good reasons involving atmospheric science to claim that we understand this. So we know that the atmosphere traps heat that's escaping to space, makes it warm, and makes it hard for Arctic sea ice to form, right? So it's kind of a straightforward story of the air temperature goes up, and then it's harder for the sea ice to grow, and it's easier for it to melt, so the area covered by sea ice goes down. That's what's happening in the Arctic. But then we have this mystery in Antarctica of what is going on when you plot the same graph. So here is a graph of the annual minimum sea ice coverage in Antarctica. And it is not a simple story at all. It's kind of wobbling around, and until 2016, it looks like it's going up. People and it was going up, right? The minimum extent of Antarctic sea ice was going up in the 1979 to 2015 period. And people on blogs were drawing lines through the graph and saying that climate change wasn't really happening, and actually, did you know that the ice in Antarctica was growing? And one of the ways I now think of it now is when the Titanic hit this iceberg. If you were on the back of the iceberg, if you were at the bottom of the world, you started to go up. And you started to say, well, I don't think we're really sinking, guys, as the stern of the ship lifts up into the air. And then suddenly, we saw this very dramatic drop-off in 2016, and we don't appear to have recovered from it. So something happened in 2016 that we have not recovered from. And there is some evidence that there was a change in the oceanography, so maybe the temperature of the upper ocean below the sea ice increased for some reason. Maybe warm water was brought up from the depths of the ocean, or it was warmed by the sun. But something's happened. And here's a plot of the same graph for the annual maximum extent. And it's actually even more stark. People get fixated on the annual minimum extent, but the annual maximum extent is almost it is, I would suggest, a more shocking story, where we're missing a huge area now compared to the 20th century mean of 2 million square kilometers. It really is a very big area that seems to have melted into the sea. So why is that happening? The final graph, and I appreciate this is a bit tortured by graph at the moment, is these last 2 years. I'm going to show you the seasonal evolution, so day by day, how did sea ice grow in 2023 and 2024. And you can see that it's not just the annual minimum, which is here, or the annual maximum, which is here, particularly for 2023, which is this red line. It's every single day of the growth season between March and September was a record low, and it actually just got worse and worse until we saw a record bad maximum in late 2023. And this was a heck of a year for me to go and spend 8 months in Antarctica in 2023, because the ice conditions were just terrible. So that was an interesting year for me, but I'll talk about that later. We'd really like to know what's going on here, and why is it not doing the thing that the Arctic is doing? Right? Why did Arctic sea ice decline linearly as expected, as models show, and Antarctic sea ice kind of went up and then dropped off a cliff in a way that our climate models that we rely on for projections to the end of the century do not simulate properly? So there's a question of why is the world like it is, and then there's also a even more unnerving question of why don't we understand what the world is going to do? Why can't we model it? So stick around, I guess. Here is maybe a little bit of context about why Antarctic sea ice might be different. So these are maps of Antarctica at the minimum and the maximum sea ice coverage every year. And this is the same plots for the Arctic. And don't forget the seasons backwards in Antarctica. So you can see the key thing about Antarctica is that it is land surrounded by ocean. It is an island, right? Whereas the Arctic is an ocean surrounded by land. And that has really, really profound differences for the way the sea ice behaves and the way it's treated by the atmosphere of the ocean. Some of the impacts of that are here. So the sea ice around Antarctica, it cannot be at the pole. The pole is covered by a giant ice sheet. So polar sea ice doesn't really exist in a strict sense in Antarctica. Instead, it's at a much lower latitude. Like it's far, far more northerly. It's far further towards the equator. So it experiences much warmer air temperatures. That means that the frequency by which the snow is typically experiences a day or two of melt in the winter is maybe higher, but also the temperature it experiences in the summer when it is actively melting are also higher. It's also much snowier. So you can imagine if you are a weather system moving towards Antarctica, there's potentially a lot of evaporation over what is basically just open ocean around the sea ice. So we see a lot of evaporation, and then when the weather system moves over the sea ice, it just dumps snow super hard in much greater volumes than we typically see on Antarctic sea ice. So it is snowier, and the snow on the sea ice is deeper. And a lot of my talk is going to be about that. One thing you also might observe is that it's more seasonal, and by seasonal I mean the difference between the winter and the summer is greater. So Antarctic sea ice melts right back to a tiny core really in a place called the Weddell Sea, and a little bit around the Ross Sea at the end of summer. It really is almost entirely destroyed by these actually warmer temperatures in summer than the Arctic experiences. Whereas the Arctic, it retreats back to a much bigger core. So there's parts of Arctic sea ice that survive every year on year, and certainly 30 years ago you could go out and you could find 5 or even 6-year-old ice floes out there. Whereas Antarctica really not so much. The vast majority of sea ice that you see at the annual maximum was not around at the preceding minimum. So that means its properties are actually quite different. And finally, Antarctic sea ice is unconstrained by land. And you might think I've already said this, but it has a profound implication for what happens when the wind blows. So when the wind blows onto this sea ice, it literally cannot move. It is stuck. The only place it can come out is through this little bit here, the Bering Strait, and through the European side of the Arctic. And incidentally, that's where we've seen the most retreat. But other than that, it's very resilient to wind. Whereas when the wind blows on Antarctic sea ice, it blows it further north. It blows it towards the equator quite often. Can't blow it further south towards the pole because there is land there. But basically all around, there is an ice edge that is an interface with water. Whereas in the Arctic, there is an ice edge that is an interface with land. So Antarctic sea ice is very, very vulnerable to the wind in a way that Arctic sea ice is not. But I'm really going to focus in on the snow because I think the snow is playing an interesting role in the world of Antarctic sea ice, and it's what's occupied me for the last several years. So part 2 of this presentation is going to be about this stuff here, the snow cover. This is a campaign in that little core that I showed of the Weddell Sea, where Antarctic sea ice melts back in the summer to this tiny little bit in a big bay called the Weddell Sea. And the snow we found here on this remnant ice that had stuck around all summer was deep. It was 50, 60 centimetres, even a metre on some ice floes, even 1 metre 50 on ice floes, and we're not selectively picking the deepest bits. It really was, in a broad sense, very deep snow, much deeper than I've ever encountered on sea ice in the Arctic. And here's another mystery about the snow on Antarctic sea ice. It seems to not form melt ponds. And melt ponds are these little ponds that appear on the surface of sea ice when all the snow melts back and the ice basically on top collects the melted snow and actually starts to melt itself. And this is one reason you might say this is obvious. The snow is much deeper, so it just doesn't melt all the way back. But even in the parts of Antarctica that are seasonal, they appear and they disappear every year, this still seems to be the case. So a lot of the work that we've been doing is trying to figure out what is the situation with Antarctic sea ice and melt ponds. Why do we not see those, and are those playing a role in the difference that we're seeing in the climate response? Here's a graph of the snowfall that hits Antarctic sea ice in the winter. In the summer, the situation is a little bit more complicated because we often don't know whether it's falling as rain or snow or a mixed precipitation. But in the winter, you can certainly see that a sort of surface analysis implies that 3 times as much snow falls on Antarctic sea ice by weight than on Arctic sea ice. And that has an important implication for what we call the freeboard. And this is another point where I enjoy speaking to Canadians, because you generally know what the freeboard is, because, and I don't want to stereotype, but canoeing is their thing, right? So people know what I'm talking about when I say a canoe. You know the difference between a canoe and a kayak. So, I want to talk about the freeboard. If I get in a canoe, and I can sit, and I can put my hands on either side, and I can feel the difference between the waterline and the top of my canoe, right? And if my buddy who's a rugby player comes and gets in, that freeboard is going to go down. And the more people I put in my canoe, the lower the freeboard is going to get until the edge of my canoe goes under the water, right? And if my friends get in with 6 packs of beer, we're going to go even lower until the edge of the canoe is literally at the waterline, and that is what I call zero freeboard. Here is a graph of that, but with an ice floe instead of a canoe. So this is what I want you to think about. There's a block of frozen seawater, ice, and that is sitting, floating in the water. And without the snow on top, somewhere around 10%, a ninth of the ice is going to stick out of the water. But as that layer of snow accumulates on top, as your friends get in the canoe, that freeboard goes down and down. And I stole this picture from a web page that's talking about the Arctic. But if we drew this for the Antarctic, typically this distance here that I've labeled freeboard is going to be very, very small. In fact, we don't really know how much coverage of Antarctica is zero freeboard. So it's very possible that large parts of Antarctica every year exist with the ice completely submerged by the weight of overlying snow. But what happens when more snow falls, when you're at zero freeboard and more snow falls? So if you're in a canoe, it's going to sink, right? It's going to fill up with water. But an ice floe can't fill up with water. So it gets pushed down below the waterline and the base of the snow floods, right? And we call that negative freeboard. I said I toned it down on the graphs. I think this is the last graph, and it's barely a graph, so forgive me. But you can draw a line about that covers the relationship between the thickness of the ice on the bottom and the overlying snow depth on the top. And you can see when you'll have a positive freeboard and a negative freeboard. So if we have 1.5 meters thick ice and 20 centimeters of snow depth, the ice is thick enough to support the snow. So we're going to have a kind of Arctic situation where there's a little layer of snow on the top of some robust floating ice. But then if we crank that up in Antarctica, maybe to 40 centimeters, the freeboard's going to be getting lower and lower. And maybe at 50 centimeters, we hit zero freeboard. At 50 centimeters snow thickness compared to 1.5 meters ice thickness, we fully submerge the ice floe. So this 1:3 ratio is quite key. When you have 3 times the ice thickness of the overlying snow depth, you are at a zero freeboard for typical numbers, right? It's not a law of the universe, but it's a good rough rule. And in Antarctica, the snow keeps piling on quite often, and then we get a negative freeboard situation. So I'll show you a picture of what that really looks like. It often looks like this. This is something that I observed with my colleague Vishnu from the University of Calgary. Here you can see we have a 1 centimeter negative freeboard. So we put the ruler in, and the bottom of the ruler touches the ice, and the water is at the 1 centimeter level. So enough snow on here, we could maybe do a bit of maths to work out how thick the ice must be to support this known thickness of 35 centimeters. We have to support that with 1 centimeter negative freeboard. But what is interesting about when we saw this is this grey layer. Right? What is forming this grey layer of snow? And this is wet snow. At first we thought, could it have flooded and then the ice grew, so it kind of thickened the ice and it pushed out the snow out again. It doesn't, it's not that. In fact, it can't be that. This is capillary action. This is a wicking process by which the pore spaces in the snow are soaking up water like a sponge from the water line. And I have a hunch that this is seriously screwing with our work, right? This is seriously messing around with the way that we use satellite technology to monitor ice and snow of different types. I'm going to get to that later. What I want to stress to you now is the geophysical implications of this, right? So imagine you flood your sea ice a little bit, and then suddenly the snow gets really heavy. Suddenly the snow soaks up this water like a sponge. That's going to depress your freeboard even more. So this is a small tipping point, right? I think this is quite speculative stuff, but I think it's very worth considering that. Someone told me that small tipping point is a contradiction in terms, but I definitely don't think so. So I think there's a small but noticeable effect where as soon as you flood your sea ice, you tip into a flooded regime where you have this heavy wet snow and it drives down your ice a little bit more. But how can we study this? I spent 8 months in Antarctica waiting for this thing to happen, and it kind of sucked. And if we don't want to do that, we have to go out on icebreakers, burn a lot of fuel, and often show up at some sea ice that doesn't look flooded, or it was flooded like a month ago and it's all frozen now. It's hard to do that, especially if you are Canada and you don't have an Antarctic research station. There's an expedition in Canada at the moment. I think it's the first all-Canadian Antarctic research expedition by ship, which is cool. But it would still be nice if there were a way to bring a small piece of Antarctica to Canada. It would certainly save on the carbon emissions. So we've just tried to do this, actually, with an experiment at the Churchill Marine Observatory. So the Churchill Marine Observatory is in northern Manitoba. It's mostly run by the University of Manitoba, but the University of Calgary also owns part of the facility. And it is, at its core, a series of two plunge pools. They're living in Norway. I go to the sauna a lot, trying to integrate, doing my best, and they run out of the sauna and they jump in these freezing cold pools. And as soon as I showed up at this facility, I thought, oh my god, I'm back in Norway. I'm not jumping in this pool. But you definitely wouldn't want to jump in this pool because it grows sea ice. They pump seawater in from the ocean, natural seawater, and then they let it freeze. And there's a retractable roof on this facility that allows you to protect it from the quite disruptive influence of snow and wind. And then you can study the formation and maybe the flooding of sea ice in a semi-controlled environment. You can't control the air temperature, but you can control whether snow is falling, whether the wind is blowing, and you can get on the ice and you can do things that you would never be able to do in the field. When you're in Antarctica, it's very dangerous all the time. There are no polar bears, but if you're working from a land station, if that bit of sea ice breaks off from the land and drifts away, they're not going to come and get you, right? You're done. If you are maybe soaring the sea ice or you're drilling big holes that you can fall into, if there's a mishap, you're done. No one's coming to get you in winter. Whereas the flexibility that this facility allows in Manitoba allows us to simulate flooding in a way that we just couldn't get away with, basically, on real sea ice. So here's a picture of what we got up to this year. We started out by growing a thin cover of very flat sea ice, a bit like I showed you in my title slide, barely any snow in it. This is actually mostly what I would call deposition from the atmosphere rather than precipitation. So it's these crystals called frost flowers and then diamond dust, which is really when the air gets so cold that the moisture just falls out in tiny little crystals. So we had a very blank canvas to work with in this pool at the beginning of our experiment that we did last month. And we made some snow. So we went outside and we found different types of snow, hard, squeaky wind slab, and like sugary, deep, large crystals of depth all, and we applied them to the sea ice, and we shaped them like you would in a ski resort. And we did it along this strip of the pool, because covering the whole pool in that snow would have broken us. So we just kept a thin strip. And then we wanted to simulate our flooding event, so we cut it out. This is Kiledar, who's sitting in the audience, nobly working with one of the most rugged tools I've ever seen a scientist use. It's this huge saw called a Finnish ice saw with these savage barbs on it. And it just cuts through that ice, it rips right through. And we cut out that slab of snow, and we, in fact, had the right amount of snow on the slab, such that we knew that when we cut it loose, there would be a zero freeze. So we knew the thickness of the ice. You can see we drilled some holes here, and we of course knew the thickness of the snow. So we knew when we cut it out, we would be close to zero freeze. This is another thing you can't do outside. Right? You can't control the snowfall and have it be enough to get that zero freeze. And then, I mean, it's certainly difficult to control even when it is enough. It's certainly hard to understand the density. So we really controlled this situation, and we sunk it. So we cut a piece out, and we weighed it down a little bit. You can see we actually weighed it down with fish tanks full of pink seawater in the background. That's what those are. And we had a 3 centimeter negative freeboard at the peak of our flooding experiment. I hope you can see that we successfully have replicated this upward capillary action into the snow. This snow is not fresh, dry snow. This snow is salty and wet. So, from a geophysical point of view, the experiment was a success. And we did a lot of characterization. So I have some oxygen isotope stuff that I'm not going to go into, but we can talk about it afterwards. That I measured, but we also measured the change in the density and the salinity. So we were able to do a full study of this sea ice flooding event that we simulated in a tiny piece of Antarctica on the Hudson Bay in Canada. So I think that was really neat. I'm going to move on to part 3 of the talk now, where I get into a little bit about why this flooding stuff and this snow stuff in general is really important for the satellite work we do. So, this is where I discuss the third member of this photo. So this is me. This is the guy from the British Antarctic Survey. And this is what we call KUKA. This is a radar that's owned by the University of Manitoba. My old boss, Julian Struve, is one of the Canada research chairs there. And this is basically a satellite simulator that we can take out onto the sea ice, and we can simulate how a satellite sees the sea ice from above. It's a radar in a box. In fact, it's two radars in two boxes, Ku and Ka. And this is one of the satellites that it is designed to simulate. It's called Cryosat. It was launched by the European Space Agency in 2010 after a failure to launch properly of Cryosat 1 in 2006, I think. And Cryosat works like this. So it just claps, right? That's basically all it does. It claps and then it listens. And you can hear when I clap in this room that there's a bounce from the back wall. In fact, I think there's actually a bounce from this one. And when you listen to that echo come back, you can learn a lot of stuff just from clapping and listening. You can learn how far away a surface is. You can also learn about what it's made of, how rough it is. So if I clap and there's a rough wall, the return, the echo of that clap will be quieter, but it will also be spread out. It will kind of be smeared in time, so it's not clearly recognizable. If I shouted someone's name, I might not be able to understand the name in the reflection. Whereas if it was a very smooth wall, I would be able to say someone's name. I'd say John, and then I hear John later. So you learn a lot from a reflection. So Cryosat claps, but rather than sonically with audible waves, it does it with radar waves, and it just listens for the returns, these blue waves. And we hope that the radar waves will go through the snow on top, they'll penetrate it, just like sound can penetrate some materials, and the radar waves will bounce off the sea ice and return to the instrument. And from that we'll learn how far away the target is and what it's made of. So you can imagine you're chugging along, Cryosat, right? And you're hearing these kind of muffled reflections from nearby. That is a reflection from the sea ice. Sea ice is a rough surface, it makes quiet echoes, and the echoes come quickly because it's kind of nearer to the sea. But occasionally you'll clap and you'll hear a crisp, loud echo that is basically an exact replica of the sound or the radar wave that you emit. And that is an echo from the sea. So Cryosat orbits the Earth, like this, clapping away, and it is measuring the range to targets, and some of them are sea ice and some of them are the ocean. And the difference in the distance that it calculates between the sea ice and the ocean is the freeboard. This key thing is the distance that the canoe sticks out of the water. And we know that the freeboard represents the thickness in some way. When the freeboard is thicker, the ice is probably thicker. So we can make maps. We can make maps of what we think the sea ice thickness is based on this technique. And it's neat, right? And we know it works because we have evaluation, we have these upward-looking sonar moorings, people are going out, drilling holes in it, we have clever induction-based methods to work out the thickness, a whole bunch of ways. We know it's not perfect. A lot of my PhD was involved in investigating the ways in which it's not perfect. I promise you it isn't, but it does seem to work. So why don't we understand this Antarctic mystery by doing the same thing in Antarctica? Why don't we understand the causes and responses of this massive climate shift in Antarctica, this sea ice drop-off, by making this map for Antarctica? Well, it's simple. So the snow properties in Antarctica are potentially very different. As I've said, it's warmer, the snow is deeper, we often get flooding. So here are some photos that I have taken in Antarctica over the last few years. And this is snow, right? This is not a picture of a sea ice core. This is really hard snow at the top of a core that just slowly turns into like liquid fresh ice, melted snow at the bottom. And when you're dealing with that, what is Cryosat clapping and listening to? Is it listening to the top of this melted layer of snow, or is it somehow getting down to the sea ice? It gets very murky. But we also get these melt lenses, right? We get these warm weather systems coming in off the Southern Ocean in a way they don't really do for the Arctic, and melting layers of the snow. And that again is going to block the radar waves. So it's going to cause problems where cryosat's going to clap, and then it's going to hear a bit of an echo from this layer, and then it's going to hear another echo, maybe from the ice surface, or maybe from some of this stuff near the bottom. It really complicates the situation. And finally, we have some other stuff. So we have the texture of the snow surface and the roughness of the ice surface. It's very difficult to know what those are in Antarctica. There's a real paucity of in situ data for Antarctica to help us understand snow geophysics. But we try, right? So I went. Here's me and Vishnu with the cryosat simulator question mark, and we can point at a flooded snow on sea ice event, and we can learn about it. Right? The last 5 years of my life have been traveling around with this instrument. I'm pointing at the radar, not this man, and pointing it at snow on sea ice in different places. And it's been great, and I'm going to kind of transition into talking about that now, rather than going on and on about the science. But first I'll show you some stuff. So we of course brought this instrument to the Churchill Marine Observatory, and we used it to scan our strip of manufactured snow. And we scanned it before and after the flooding event, so hopefully we can now look at that data and maybe even make a flood detection algorithm. Maybe we can do something with cryosat, some signal processing method to help us learn when we're looking at flooded sea ice and when we're looking at dry sea ice, because that would be so useful. Because once the sea ice is flooded, you're done, right? You can't look at how far the canoe sticks out of the water and figure out how big the canoe is. It just doesn't happen. And in fact, if you try, you get sensible answers that are wrong. So it's not like you get a billion or you get like negative sea ice thickness. You get numbers that look right and are wrong. So this is a neat example of one of the facilities of Sierra. It has this movable gantry that we can mount instruments on and profile the snow and the sea ice in the tank. That's John, actually, who's in the audience. Here is also John, also in Churchill, but in a different year. We can tow this radar behind a sled and generate quite long transects of data. We can study with very high resolution, with in situ observations, the radar backscatter from snow and sea ice. So the sled facility is good. We can do crazy stuff like this. So an Antarctic campaign in 2022, they would land the helicopter here, they'd drop us off on an ice floe. You can see the runners, the marks from the runners of the helicopter in the snow. And we would unpack Kuka. This is actually Kuka here, this is the stand. We would build it on the floe, we would study the properties of this drifting ice floe. So confusing because as well as drifting sideways, the floe is rotating in space. You lose your orientation very, very quickly in this environment. And then at the end of the day, we call them up on the satellite phone, they come out and get us and pick us up. And that was probably the coolest thing I've ever done in my life, I'll be honest with you. Another way of using Kuka is like this. We can't always land on the sea ice. These are pancake ice floes. They're very small ice floes, maybe 30 centimeters thick, a few meters wide at the biggest. We can use a crane to investigate the radar signatures of these pancake ice floes, and again build a detection system. So we can get out there with cryosat and tell what cryosat is looking. Is it looking at a plate of ice, or is it looking at a rough mixture of ice floes in free drift? And the reason I wanted to show this picture is because it has these icebergs. These are a real feature of Antarctic research. The icebergs are everywhere. I didn't realise this until I went, but they are like densely packed in some parts of the Southern Ocean in a way that I found absolutely stunning. But the final campaign I wanted to describe was this one. I took this photo out of a plane as I left after 8 months, where Vishnu from the University of Calgary and I stayed in this little research station here. I think I've got it. Green, yeah. And this is the British Antarctic station called Rothera Research Station that exists on the Antarctic Peninsula. And if you imagine Antarctica is a big round island with a little tail, this station is halfway up the tail. It's actually at about the same latitude, 68, 69 degrees south that I live at now in Norway. And we spent a long time there. And this is what it looks like in the summer, when all the snow melts away. It's basically a runway with a little village connected to it. But in the winter it is a very different place, because it's dark for a lot of the time. But also, the weather in this place is like nothing I've ever experienced. And as I say, I live at the same latitude now, just in the northern hemisphere, and my experience is not the same. So the amount of snow that you have to get used to is obscene. So you will show up in the morning and a door will just be completely drifted in, and then you need to dig it out, because to fire exit, it's the way to move between the buildings. These research stations aren't just one giant building. There are many small buildings where you move between throughout the day. If you do not love to dig, you should not go to coastal Antarctica, let me tell you. And hopefully this really drives home the amount of snow that the sea ice can experience. Right? When we are experiencing this, the sea ice next door is also experiencing this. It is also windy. This is Vishnu on not an atypical day in a blizzard. You can't go out on the sea ice in these conditions, it's too dangerous, but you do have to get stuff done, right? You have to dig out these shipping containers, which is where we store the food. You have to make sure that the station's power plant is operating effectively, because the exhaust get covered with snow. You have to do all kinds of things to keep the station going, basically. So you can't escape. But there's also amazing science. So there's good weather days where scientists will go scuba diving under the sea ice, and they'll collect samples. You can see them passing out samples here. And they're doing incredible research into the changing oceanography of Antarctica, but also they're looking at the way these icebergs scour the marine bed, and they destroy the coral and the sea sponges and things like that grow in the benthic environment. So all kinds of amazing work is being done year round through the winter in this place. And you can help. So Vishnu and I would occasionally go and help the marine team do their CTD casts. CTD is conductivity, depth and temperature, and it profiles the ocean. So we learn about how is the intermediate, the surface of the deep ocean warming with this data. And have a really long time series. I think it's decades long at least for Robin. So it's great to do your own science about Antarctic snow and sea ice, but it's also great to be involved in other science. And there's a really nice community of people that do the science but also support it. So there is a social scene. It's kind of cozy. You work hard to light candles some evenings and put these flags up, and you make the best of what is often a tough situation in the winter. And there's a lot of flexibility as well. So we live in an understandable culture of health and safety, where employees can have confidence that they're going to do their jobs and not get hurt. But the bets are somewhat off in Antarctic winter. So you crowd into the garage along the snow machines, and you can watch the Wimbledon final, and you can do things that you would otherwise perhaps not do in a sort of in a community spirit that I really loved while I was down there. And I think you have to do this because the environment is so harsh and it's so hard that if you don't do this, you fall apart. And there are stories of wintering Antarctic teams that absolutely do fall apart. So the community spirit and the flexibility, this was a big effort from the guys that run the garage to facilitate this. And people just do it. People work hard to make wintering in Antarctica work. So that is my last slide. Thank you for coming and thank you for listening. This is skiing among the icebergs on Antarctic sea ice. This was my one day where I had fun on the sea ice in a recreational sense. I got one day where I went out and just tried to enjoy myself and didn't think about digging the snow. So yeah, thank you very much for coming.
Yeah, thanks, Robbie. That was terrific. We've got some time for questions. So who would like to ask a question of any kind?
About
Yeah.
the one question, the Tongo volcanic eruption. which was in 22, basically stated that there'd be 5 years of warming following it, and then of course your 2 dates of lack of sea ice. Is there a correlation?
Probably not, but a lot of people have thought very hard, so that there is a warming impact, and it's probably less than a decimal point of a degree. What was interesting while we were here in 2023 is that this eruption put a lot of water vapor into the stratosphere, and the water vapor hangs there. The stratosphere is not well mixed, it's not overturning, it's stratified, it's in the name. And it takes a year or 2 years for stuff to rain out. So we had these things, and I almost put a photo in, I wish I had now. We had these stratospheric polar clouds that are very thin, and they're rainbow coloured because they're translucent, they're partially transparent. And they were just there for days. And of course it's nighttime, but the sun is slightly below the horizon. So for days, and sometimes even weeks at a time, we would have these bizarre cloud formations, potentially related to this eruption that had happened just before, of these like rainbow coloured clouds in the night, just shining down at us. It was totally bizarre. They're called nacreous clouds, if anyone wants to look at them. So yeah, that eruption played a big role in the conversation around their table.
In the first picture you showed with the water being whipped up into the snowpack, it looked like there was standing water and then a dark layer and a lighter layer, and then everything above the capillary was gone.
Yeah.
That dark layer, is that just a saturated zone, or is there something special about that bottom few centimeters?
It's actually pretty homogeneous in the samples we've taken. I think that's an optical effect of basically it's kind of just darker, there's less sunlight near the bottom. But the material properties of this grey layer appear to be fairly homogeneous. The only interesting thing is that it appears the salinity does actually go up with height, which you would not expect. And my only theory about that, I don't think this is even my theory, it's one of my colleagues, is that maybe it froze, and when seawater freezes it rejects brine. And if this layer potentially froze before we got to it, it would have rejected some brine into this pool where it would have dispersed, and it would maybe have rejected some brine upwards where it potentially couldn't climb any further. So we do have some interesting like layered stuff going on here where the salinity appears to go up at the top. But this is all fresh snow, so all this white stuff near zero salinity. And you can see there's a layer of like fresh powder right at the top. You might be able to see this line.
What's the spatial variability like?
Big.
A meter, 10 meters, 100 meters away?
It made it really hard to study because our modus operandi on the sea ice is to show up with radar, do a scan, and then dig a snow pit where we've scanned. And we knew that there was a negative freeboard, but we would often show up with the radar, scan it, dig the snow pit, find that there was no flooding there, despite the fact that we knew the ice was below the water. So there's big questions of how does this water get in? Does it come up through tiny cracks in the ice, or does it perfuse through the pore structure of the ice? And we know that at warm temperatures you get connected brine channels in the sea ice. They're like capillaries in your arm that brine can move up through. But why is it so variable if that's the process? So there's a lot of you can take 2 steps to the right and you'll have a totally different situation, at least in my experience.
There's lots of work that's been done on lake ice with that. Because the same thing, negative freeboard happens on lake ice all the time.
Yeah,
And it weights it down, and you can sometimes you hear people talking about they hear that their lake could crack, and then you don't want to go onto the lake after the crack because the water's flooded up into the snow.
We experienced this actually. After our experiment at CMO, the Cheshire Marine Observatory, we took Kuka out onto a nearby lake because we're also interested in lake ice thickness, determining it from space, and we characterized the snow, we dug our snow bits, and then the time came to figure out how thick the ice was, and we drilled the ice for thickness, and it just gushed out. So there was a negative freeboard, and it really poured out of that hole that we drilled in the lake. So yeah, I've had somewhat bitter experience of that in the last fortnight.
Again for coming, and let's thank Dr. Melick once again. Thanks again. Feel free to come by and have maybe either a personal chat or grab a donut and a coffee on your way out. Thanks, everybody.
Very nice talk.
Thanks.
Nice work to